Thanks, Jonathan.
Thanks, Mike. Good morning, everyone. So the slide here shows some stills from some videos that we've produced that support the National Geological Screening that I shall talk a bit about a little bit later, that we worked with the British Geological Survey on. And really this plays to one of the two sort of principal categories of the ways of the role of geological science in supporting the whole process of the radioactive, the geological disposal, the deep geological disposal program. And those categories are technical, and they're also what Nick spent most of his time talking about, and that is the public communication piece, the idea that UK policy is based on public consent. And we've seen with the fracking debate, for example, that there's a real hunger for knowledge, not necessarily advice, but good quality, authoritative, objective information. So we produced a number of videos that support the narratives that we produced as part of the National Geological Screening. So before just saying a few words, I'm going to talk about those two broad categories of the role of geological science in deep geological disposal, technical and the social and public consent piece. But before I do that, I'll just say a few words of introduction. So some of you will know that just before Christmas, BEIS, the English government, published the Working with Communities policy. And the Welsh Government did the same just last week, which means that we are now formally in a site selection process. So RWM, for the first time in a good number of years, is now in a campaign. And that's obviously incredibly exciting for us, and I think it's very exciting for the UK. In terms of the justifications for geological disposal facility, traditionally, there are three of them, I would argue four really. Traditionally, the three justifications, the burning platform, if you like, is cost, security, and intergenerational equity. But the fourth, and I think the reason why I've been invited by the conveners to speak here today, is that you'll know that nuclear is an integral part of the government's industrial strategy. And for 40 years, and then enshrined in law for the last 20 years, the government has been required, in order to proceed with a nuclear new build program, to have a recognised solution for the disposal of the products of that nuclear new build. So really, geological disposal is an integral part of decarbonisation, which is the theme of this conference. So the top bullet point there, I think, is a really important point. So RWM is wholly owned by the Nuclear Decommissioning Authority, and it's tempting to think of us as being part of the nuclear industry, but in fact I'd argue that actually we're part of the environment industry. This is a huge environment project, and the three key ingredients, all three of which need to work together in order for us to progress to a site, become a site licensed company and actually develop a facility, is we need a willing community, we need a suitable site, and we need waste which is suitably packaged. And really, geological sciences speaks to the first two of those. It plays directly into the public understanding of what it is that we're trying to do, and also selecting and characterizing and giving our stakeholders, including the general public, confidence that we really have a site that's going to have integrity over the hundreds of thousands of years post-closure period. The 2 points at the bottom there, it's highly engineered. The word that I'm trying to avoid there, which we see crop up so often in the media, is dump. And I understand why that word is used. Geological disposal facility, I think it's 12 syllables. Dump is a single syllable. The last one there, storage. So I think dump is often used mischievously. Storage, which you'll also see very often used in the media, I think reflects a genuine lack of understanding. So I just emphasise that the government's deep geological disposal program is about permanent disposal. It's not about storage. So unlike the French, for example, we don't incorporate retrievability. The schematic, and I emphasise that it is very much a schematic diagram. It's just giving a flavour of what a GDF, a geological disposal facility, might look like. So about up to 2 square kilometres surface footprint, up to 20 square kilometres subsurface footprint, and the the vaults and tunnels will be between, or certainly no shallower than 200 metres below the surface, unlikely to need to go deeper than 1,000 metres. When you look at other countries, most of their facilities are around 500 metres. So I emphasise this is definitely not to scale. And you can see the intermediate level, sorry, the high level waste on the left-hand side here, and the volumetrically larger but smaller footprint intermediate level, i.e. non-heat generating waste on the right-hand side of the diagram there. I emphasise it is an artist's impression. It's a public consent-based process. Until we have communities, working groups, community partnerships that we can work with and begin to evaluate their sites, the level of uncertainty within which we operate at the moment is very high. So this shows a sort of highly sanitized, can't really recognize anywhere in the UK here. Just to make the point, it could be onshore, it could be offshore. Obviously, there's a variety of different geologies. The surface facilities might be vertically above the tunnels and vaults, or they might be laterally displaced from one another. There's all sorts of factors which mean that this schematic situation could change according to what communities come forward with. We will evaluate what we've got to work with. Okay, so the first slide that I showed with these stills from the videos, I mentioned that those videos, and there's a whole bunch of other sort of public communication devices that were produced as part of the National Geological Screening, which is a description of the geology of England, Wales, Northern Ireland as it relates to safety for a GDF. It was produced for RWM by the British Geological Survey. The eye-catching graphic here is the BGS's UK 3D sort of fence diagram of cross-sections, which is another device that they've produced. It's on their website, just been published, I think, or just been made available. I think another device for helping the public to understand the technicalities of the case that we're making. Just briefly mention that the rich diversity of UK geology is broken down into three main categories of potential host rock. There's what we call high-strength rock, which is low matrix permeability, but the possibility of advective transport of fluids through fractures. There's clay-type, low-strength sedimentary rocks, where water moves very slowly, dominantly by diffusion. And then the third category, which doesn't really fit into any of the other two, is salt, which is generally impermeable and very dry. So one of the ways in which, there are three ways in which we can look at other examples to help the public understand the technical case that we're making for a geological disposal facility. So there are natural analogues. We can look at what other industries have done, and also a very common question that the public ask is, are other countries doing it? So I'll deal with the first of those first. Natural analogues are a really useful way of reassuring and sort of conveying the challenge that we're faced with. And this is one which you'll often see here. It's the Cigar Lake uranium, high-grade uranium ore body in Canada, 1.3 billion years old. The uranium ore, you can't really see the details here, but it's encased in a low permeability clay, and there's no trace of radionuclides at the surface here. So a nice sort of natural example of a sort of a natural GDF, if you like. Are other countries doing this? Well, one of the benefits that RWM, one of the benefits that the UK gets from being behind the curve compared to most other countries that are facing this challenge is that we can learn from how they've gone through their program, and we can also use their programs, which are in various stages of maturity, to convey the point that, yes, indeed, other countries are doing it. So this is an example from France. They're constructing their facility in a Colovian Oxfordian sort of super low permeability mudstone. They do incorporate retrievability into their system. So this is a sort of lab scale, full scale mock-up of their sort of push me, pull me vehicle for not only pushing the canisters into the tunnels, but also retrieving them over a 150-year period if need be. And then thirdly, and this really plays to one of the points that Nick made right at the start of his talk, I think you were talking in the context of health and safety. I think it's very useful to understand that whilst GDF is a first-of-a-kind project for the UK, many of the challenges, both technical and social, that we face have been undertaken by other industries. So what in business schools they call reference class forecasting. And an example I use here is the oil and gas industry. They've engaged in recent years, especially in some of the challenging societal debates, some of which we're talking about at this conference. They obviously do health, safety, and the environment really well. They are used to delivering major programs, albeit on a different timescale to the timescale to which we work. They manage risk and uncertainty, and obviously they understand the subsurface. They're good at conveying what the subsurface is and probing the subsurface with seismic surveys and deep drilling, much the same way as we do. The graphic I show here, clearly it's a reservoir model, not so different to the sort of site descriptive model that we will produce once we've down selected to 2 sites and we carry out a really detailed characterization of those 2 sites, which I'll talk about a little bit later. It's just a brief point which I want to make, and again, I think this plays to the theme of Nick's talk that we've just heard, and that is clearly we want people who are curious about our mission to come to our website, phone us up, talk to us, look at the National Geological screening. Our values include accessibility and trust and open communication. I think that's the only way that this project is going to actually finally deliver a GDF for the UK. But I think the role of the learned societies and the Geological Society being one of them is absolutely critical. And the words that I put in the bullet points here are taken directly from their 10-year strategy and from their recently published mission statement. Similarly with fracking, I think very often what the general public want is not advice, but they want high-quality, objective information. So many of us must have been in that situation. I don't know, Christmas parties, as soon as you say that you're a geologist, people are straight on to you, tell me about this fracking. They don't necessarily want to know, is it right or is it wrong? What they want to know is what fracking actually is, because they get very conflicting views. So we can tell them that. The general public might say, well, RWM would say that. I think the learned societies are going to continue to play a critical role and maintaining that impartiality, and that's why I put that first. Really important. So I've pretty much finished talking about the first of my 2 categories of the role of geological sciences and indeed the geological science community in helping to progress the deep geological disposal program for the UK. And so I'm now going to talk about just give examples of some of the technical aspects of what we're doing and clearly the critical role that geology will play in delivering the technical program. So to start with, I just want to really emphasize, these, for me, the 3 bullet points there highlight what a geological disposal facility is about. It's about containment, in other words, containing the radionuclides such that they can't migrate to the shallow subsurface where they can enter the biosphere, they can harm people and the environment. It's about isolating the nuclear materials, both from human intrusion, inadvertent human intrusion by future generations and even future civilizations. And it's also about isolating the nuclear material from surface processes. In the UK, we don't have active volcanism, at least not over our post-closure safety case time period, unlike Yucca Mountain in the US, for example. But clearly, when you're dealing with a 100,000-year plus period, then glaciations and substantial climate change is a certainty. So containment, isolation. And then the last point I'd make, which really plays to the point I made earlier about the fact that this is permanent disposal and not storage, and that is about passive safety. The facility will be sufficiently well engineered such that it will be decommissioned, backfilled, and I dare say there will be monitoring systems that will be installed as part of the facility that's delivered. But essentially, it's about passive safety. So it's a bit of a complicated diagram, but actually there's a really simple point that comes out of it. In terms of geological sciences, the sort of big ticket delivery on the horizon for RWM and for the geoscience group within RWM is the site characterization phase. So we're presently in a site evaluation phase. We're talking to would-be communities. That will then progress to working groups, and then those will progress yet again to what are called community partnerships. So the process becomes more formalized, and there's community investment as we continue through that process. But the planning assumption is about 5 years from now, we will have down-selected to 2 sites, at which point RWM will turn into really a mini oil and gas company, contracting 3D seismic crews, drilling rigs, airborne geophysics. So in other words, producing what we call a site descriptive model. Probably the most detailed subsurface characterizations of these 2 pieces of real estate that will exist for the UK continental shelf. And what the diagram shows with the site descriptive model sort of cartoonized in the middle here is this iterative loop of initial data, understanding the requirements and concepts based on the geology and the characteristics of the local area, engineering designs, the safety case. This word safety has special connotations in the geological disposal industry, and that safety in this case refers to the transport, operational, and post-closure safety cases. And then further information, further phases of drilling, geophysical data acquisition, and so forth. So the main sources of data that will feed into that site descriptive model are boreholes, as we saw, for example, 20 years ago, the boreholes that were drilled as part of the evaluation of the proposed rock characterization facility up there. Geophysics, 2D and 3D. So look at some of our overseas counterparts, and they've put a lot of effort into acquiring high-quality geophysical data, which means that for some of them, the boreholes that they're drilling are essentially confirmatory. They really understand the subsurface before they do those boreholes. And then the third source of data, and the reason I left it separately, is that the point at which we down-selected and recommended to government our favoured site, and that recommendation has been accepted, that site descriptive model will forever be refined once we start going underground and start constructing the facility. So 3 sources of data that input to the site descriptive model. And that will be a huge investment of not just money, but also resource, and there will be a lot of interaction with the wider geoscience community, the British Geological Survey, academia, our overseas counterparts, and so forth, as well as the supply chain. So the examples that I'm going to show for the remainder of this talk really play to looking in detail at the role of geoscience in undertaking the post-closure safety case. So there's a lot of detail on this slide here, but as I said before, what this is addressing is the idea that when we're looking over the 100,000 year to million-year post-closure safety case, then significant climate change and glaciations are a certainty. And what this shows, what the diagram shows here, is work that we undertook with the British Geological Survey. In fact, I think, Dave, you were involved in this work. So the map is showing, it's showing the likely thickness of permafrost around the UK. The details you can't read, but as it says at the top there, we can expect up to 300-metre thicknesses of permafrost under long-term, steady-state frozen conditions. And looking at the 3 controls on development of permafrost which have gone into this model here. In other words, climatic forcing, the geology, particularly the thermal conductivity and geothermal gradients, and then advective heat transfer. So clearly it's important for RWN to understand the likely distribution of permafrost in putting together the post-closure safety case for the 2 sites that I described will be characterized as part of the site characterization phase, because, as it says in the top 2 bullet points there, the impact that permafrost has on the hydrogeological systems, and you can read those for yourselves, and I'll skip on. But just an example of how geological sciences is central to putting together the post-closure safety case. So the next 2 examples are looking again at the post-closure safety case, but looking not so much at the far field, e.g. climate change effects, but this example here and the next one looking at the near field impact of the geological disposal facility on the on the geosphere, on the immediate environment around where the GDF will be constructed. And the theme here is what are called excavation damage zones. As we saw in some of the quotes in the last talk, if you take out some volume of rock, then that's going to perturb the geosphere in various ways. And one of the ways in which it perturbs it is it will concentrate focus stress around the tunnels and vaults. And just in the same way as you get borehole breakouts in a borehole, then you'll get sort of large-scale borehole breakouts in the tunnels and vaults. So the example here is from the Swiss underground facility at Monterrey in the Jura. The Swiss have down selected to 3 sites, all 3 of them in this middle Jurassic super fine-grained opaliner clay. What's shown here are small faults and fractures that form the excavation damage zone around one of the tunnels that have been mapped just by traditional mapping techniques. The point about low-strength sedimentary rocks, of which this opaliner clay is a great example, is that the rheology, so the elastic properties of those rocks, is such that whilst they'll form excavation damage zones and faults and fractures will form as a consequence of mining into the geology, those faults and fractures will self-seal. And what this research project that's been ongoing at Monterrey, and you can see one of the tunnels here which is wired up to carry out both resistivity surveying and seismic surveying, is they're trying to understand the rate and, mainly the rate of sealing of the fractures that form as part of that excavation damage zone. So the details don't really matter. If we look at the resistivity, low resistivities, this is a cross-section through the tunnel there, low resistivities at the base of the tunnel associated with closing up of the fractures and really quite effective sealing of the fracture systems. And similarly, looking at seismic slowness, the red is faster, higher seismic velocities, the blue is lower seismic velocities, so the red zones would be areas where the fractures within the excavation damage zone had sealed. Again, like I say, the details don't matter, but it just gives you a flavour of the sort of detailed research that we, the UK, will need to, or RWM will need to undertake as part of its site characterization programme. And then lastly, again, looking at the idea of the near-field response of the geosphere, so the geosphere in that immediate environment around the geological disposal facility. And this really brings out a very important point which is worth emphasising. People often ask us, how come you're not able to say what disposal concept? So what I mean by that is the engineered barrier, the conditioning of the waste, the canisters, the buffer, and the backfill. Why are we not able to say now what engineered barrier system we'll use? And that is because, as I said in the abstract, in fact, I think I italicized it, it's really important to understand that the engineered barrier will work in tandem with the natural barrier, i.e. the geological barrier, and they will work together in order to contain the radionuclide. So to give a simple example, if we were to construct a GDF in an organic-rich clay, for example, in one of these low-strength sedimentary rocks that had a particularly high sulfide content, sulfides don't work particularly well with copper canisters, such as they're using in Sweden and Finland. So we wouldn't necessarily opt for a copper canister disposal concept if we had high sulfide content within the groundwaters. That's just a simple example. But what's shown here on the slide is really looking at the way in which the cementitious backfill, so for high-level waste, the canisters will be placed in drill holes. They'll be in sort of donuts of bentonite buffer material, and then the tunnels and vaults will be backfilled with a highly alkaline, very high pH cementitious backfill. And one of the roles of that cementitious backfill is to buffer any incoming groundwaters in order to maintain that high pH environment around the canisters. Why is high pH important? Well, because you'll know that radionuclides are least soluble in high pH, low EH environments. So the model that we can see on the left here is just modelling groundwater flow into the kind of system that I described. So you can just make out a vault in the centre here, encased in what is modelled as cementitious backfill, this high pH backfill. And we can see that as we progress from a few years to thousands of years and tens of thousands of years, in the first instance, there's a slight drop in pHD as the system equilibrates. But then as we go from the 2,500 year to 50,000 year post-closure model period, the cementitious backfill really works very well to maintain that high pH and thus the low solubility of the radionuclides. Nice example here from an alkaline plume which has migrated through sedimentary rocks in Jordan. So again, using natural analogues, nice combination really of natural analogues and in this case modelling. So I haven't got any conclusions because, to coin a phrase, it's a journey. It's a journey we've only really just started off in terms of getting into a formal site selection process. I would urge you to visit our website. We've got a really good campaign website, and quite apart from anything else, you're now able to read yourselves the results of the National Geological Screening. So thanks very much.
Okay, questions for Jonathan? I think we have time for a couple of quick questions. Question here, Bob. Oh, sorry, there's a question over there.
John Brenner. Radioactive waste comes from basically two major sources. One is nuclear weapons, and the other is nuclear energy, and then there's some minor sources. In this conference, we should be concerned about nuclear waste disposal from nuclear energy. And although the weapons waste is obviously hugely important, it's not our concern in this meeting. So can you give us a guidance as to the proportions between those two? Because what you were talking about was irrespective. You didn't mention the source of the wastes.
I didn't, yeah. In the interest of time, when I give a longer talk, I've got a really nice slide which does show the proportions, and exactly as you said there, you know, the volumes are dominated by not just spent fuel, but the products of nuclear power. There's also medicine, which on the sort of bar chart that I show, you can't even see it. It's so minor. And defence is small, but significant. Off the top of my head, I can't remember, is the honest answer, how volumetrically important defence is. But it's small. You know, it's less than 10%, and I simply can't remember them. If you like, I can get back to you and email you, because there's nothing particularly confidential about that. The point that I would make is that it depends whether you deal in volumes of packaged waste or you deal with footprint. So, for example, to take the nuclear new build programme, our inventory includes the 16 gigawatts of nuclear new build that was kicked off by the Blair government. The spent fuel from that new build programme is volumetrically fairly small, but in terms of footprint, it's a lot larger because it's so much hotter, and therefore you need more space to accommodate it. So depending on which metric you use, volume, footprint, cost, and there are others. So I can't remember. It's small, but you're absolutely right. It is a part of the inventory.
Thank you.
Bob Holdsworth again. One of the challenges, of course, that you face with geological disposal of radioactive waste is that it's a long-term project. It's a project that's going to last decades. Could you say a little bit more about that? How are you approaching that? How are you dealing with that? It's a little bit different, perhaps, to some of the others where, you know, we need, if you like, relatively rapid solutions, but this is a long-term solution.
It is, yeah. So the planning assumption is, as I said before, 5 years to down select to 2 sites, and then you can read in the 2014 white paper, 10 to 15 years to undertake that site characterization phase, and then 100 plus years of construction, filling, and decommissioning. So it is a long-term project. You know, we will long since be retired when probably when we get to construction phase, let alone finishing the project. That does present many challenges of its own. I think particularly focusing on the public engagement piece. You know, I think we need to absolutely live and breathe the openness, the accessibility, the trust, you know, the company values, because I think that's the only way that this project is going to progress. The other thing I would say about the long-scale nature of the program is, yes, I mean, I keep using this term planning assumptions, and our planning assumptions are that it will take something like 15 to 20 years to down select to a single site. But I think it's important that RWM is a part of the solution rather than the problem. What I mean by that is you can imagine scenarios, political, global, whatever, in which the government turned around to us and said, can you do it quicker? Yes, we can. It will probably cost more. You know, there would be other things we would need to change in terms of our plan, but so that's the planning assumption, but in principle, we could do it quicker. And also, depending on the nature of the geology that we need to characterize, that 15 and 20 years could reduce quite substantially. But I mean, you're right, it does, the long-term scale of the project does present many problems which are pretty much unique to GDF. You know, I drew the parallel with oil and gas, but oil and gas, by and large, goes into a new exploration license, and within 2, 3, 4 years, they need to have acquired seismic, drilled a well, and be in a position to relinquish some of that acreage. You know, those are timescales that are completely alien to us.
Okay, thank you. So you've got a very big Gantt chart, I guess.
Very big Gantt charts.
So David Jenkins, I used to be with BP, it was a long time ago. Is this working?
Yeah.
I think it is. You said 5 years to select 2 sites. My point is, how are you going to make it worth the community's while to have a site underneath them or near them? How much are we going to pay for it? You're going to pay them for it, because they won't want it. Absolutely guaranteed.
Yeah, interestingly, this is not unrelated to Bob's question. So the working with communities policy lays out that once we get to what's called the community partnership stage, where we have a working group that includes at least one principal local authority and the landowners and so forth, that's the point at which those communities will receive £1 million a year, and then when we get to site characterization, when we've down selected to 2 sites, it will be increased to £2.5 million a year. And I think the reason for that community investment, I mean, in the grand scheme of things, those are not very large amounts of money. The big prize is the long-term jobs and investment and, you know, all that stuff. But of course, because it's such a long-term project, the people who are giving their permission for this project to go ahead now, they won't actually receive those benefits. So that's the logic behind, I mean, obviously we're open to people saying they're just bribing the local community. I think not. What we're doing is acknowledging that they won't see the benefits, the long-term 160-year plus benefits. I went to the US facility in New Mexico last year, and so it's about 50 kilometers from Carlsbad in the Permian Basin. They're presently got a sort of Steinbeckian gold rush going on with, they've got a new gas shale, the oil shale, I think, that they're exploiting, but they're still really keen on geological disposal because they recognize that oil and gas waxes and wanes, whereas they're dealing with 100-year plus, long-term investment, jobs and jobs and infrastructure.
Okay, thanks, Jonathan. I think since we are running behind time, we'll move to the next talk.